Now the recap was we did entropy, which was a measure of the disorder of a system, and you had high entropy states, which meant that they were very disordered states, and you had low entropy states, which were very ordered. Can I give you an example of a neat and tidy room versus an untidy room? And I told you that this is a high entropy state, this is a low entropy state, and I told you that we are interested in things known as delta S, which could be positive. That means there is a gain of entropy. Okay, let me delta S. I mean, it's written over here. Delta S positive means that the entropy is increasing. Vice versa, there's delta S negative, which means you go from a, a, a more disordered state to a less disordered state. So that's delta S negative. And we talked about things like systems, they like to gain entropy, which means that it's a lot easier for a neat room to go into an untidy state. I mean, it happens naturally. And it's a lot more difficult to actually go from an untidy state to a neat and tidy state. And that could be applied to pretty much anything that's any process that's happening in the world. You buy a car, and it would eventually break down. It would deteriorate. It would go into a more high entropy state. Not the other way around. You don't buy an old car and it sort of starts moving by itself into a more disordered, more ordered state.
सर आप पहले से समझा सकते हैं कि what is entropy? I didn't get.
I said just very quickly, entropy is disorder, simply disorder. Okay. Even what we did yesterday, we didn't do any details about it. We just said it's disordered. Okay. Untidy room, tidy room. This is low entropy. This is high entropy. Ibrar, is this clear?
ठीक है सर.
Okay. And I told you that high entropy states are very stable. And if you have an untidy room, it would remain untidy, right? So it's a stable state. It won't change. But if you have a neat room, the, keeping it in a neat and tidy state, keeping it in a low entropy state, it's kind of difficult. Your room would eventually uh, move towards a high entropy state. I mean, things like to go towards high entropy state. Low entropy states are very unstable. You buy a brand new car, so maintaining it in that low entropy state, it's kind of difficult. It would eventually move to a high entropy state. It's going to become an old car, and it's going to break down. I mean, overall, it's going to become more disordered. So, so things, they like high entropy states. They are more stable. Uh, like if you buy an old car and it's broken down, it would maintain its state. I mean, it's not that. I mean, it would either, if it's possible for it, it would try to gain more entropy. Uh, but something that's already disordered would maintain its state. It would maintain its disordered state. It won't move towards a low entropy state. As anyways, you need to know the sign of delta S, which is it could be positive, it could be negative. So if a process has a positive delta S, that means that the entropy is increasing. If the delta S is negative, that means the entropy is decreasing. And systems like delta S positive. They like to go towards high entropy or more disordered state. Uh,
So the S represents entropy or a system.
the S represents entropy. Okay? S is the symbol of entropy. Okay? Achha, so one thing is that we learned yesterday was we can apply the same concept to chemical reactions. We know that systems, they like to gain entropy. They want to go into a more disordered state. They want to go into a more stable state. So they would. So how do you figure out in a chemical reaction? How do you figure out whether entropy is increasing or decreasing? So one of the things that we discussed was that you got solids, and you got liquids, and you've got gases. So if there's a change of state that's happening, gases are more disordered. So that's a high entropy state, and gases are very high entropy. Solids and liquids, on the other hand, are low entropy states. They are less disordered. And this is how entropy would change. If you plot the entropy of water from minus 10 degrees centigrade to zero, it's a solid. It's in solid state. It's in the form of ice. So its entropy barely increases. Uh, I mean, ice at minus 100, ice at minus 150, ice if it's at minus 200, the particles are still exactly arranged in the same way. So, so they're not becoming disorderly. They're not changing the entropy of the system. But as soon as you hit zero, ice starts to melt. This happens, and all of a sudden, the liquid water is at a higher entropy. It's more disordered. And then you have liquid water. You start heating it. You give it energy, and pretty much nothing happens to it up till this point when it reaches 100. Like if you see liquid water at 10 degrees centigrade and you see liquid water at, for example, 80 degrees centigrade, unless you don't touch it, you can't really uh, guess which one is more disorderly because they're almost the same. They're still liquid water. But as soon as you hit 100, there's all of a sudden there's this drastic change in the disorder of the system. It changes into a gas, and the particles are now really, really disordered. They're highly disordered. So, so entropies, change of state. That's one thing. Then in a chemical reaction, I told you that you got if more gases are being formed. So I told you, I gave you the example of octane. If you have more gases being formed, that means entropy is increasing. More gas modes are formed. So there's a lot more disorder being created because gases are very, very disorderly. So if you, the more gas you have, I mean, it's the same concept. The more gas you have, the more disorderly the particles are. So if in a reaction, solids are turning into gases or liquids are turning into gases, or the moles or the amount of gas is increasing, that means the disorder of the system is actually increasing. And then there are other things. If you're trying to dissolve a solid, uh, then it changes into aqueous. So that's again an increase in disorder. Okay, so we did some questions about this. So you should be able to figure out. We did questions and it was very simple. We'll do those questions again. So we're going to move towards. I said, did I discuss why do you want to measure delta S? Or did I discuss why delta S was important? Anyone, did we discuss this yesterday?
No.
Okay, so we did not discuss this. So why are we trying to figure out whether disorder is increasing or decreasing? Like why do we care? Why do we care that water, like liquid water, is its disorder increases when you reach 0 degrees centigrade, and it increases again when when it reaches 100 degrees centigrade. So we did try to figure out. We did some questions, and we did try to figure out the sign of delta S, whether it's positive or whether it's negative. But and mostly by just looking at the reaction, you can figure out whether delta S is positive or negative. But why is delta S so important? So that's a very important question. Now the thing with delta S is that delta S is related to useful work done. So whenever you have a system or whenever you have a chemical reaction that's happening, the chemical reaction does two things. Uh, I mean, you do any chemical reaction, it does two things. There is an enthalpy change, delta H. So heat is produced or it's released. So either the two things would happen, produced or taken in, right? So for example, you burn a match and you see fire and there is heat being produced. Uh, but that heat is kind of very useless. I mean, you can't really do much with heat. And remember this, delta H is overall kind of not very important. Like you can't really convert that into useful work done. And when you do a chemical reaction, another thing that happens is the entropy changes of the system. Like if you boil water, that's disorder increasing. So delta S could be, it could be positive, it could be negative. Now when disorder is created, work can be produced. Work is produced in useful work. You can't really do much with the heat that is produced. So you get a useful work is either taken in or
Say, will heat be always being produced or will it also be released?
nee,
So, yeah,
produced or taken in. No?
अच्छा, okay. So,
This one. Remember this, whenever you have a chemical reaction, okay, like burning a match, two things happen. Uh, Either heat is produced or taken in, so that's like the temperature increasing or decreasing. So that is one thing. And the so if you burn a match, it produces heat. There's a flame. And the other one is when you have a chemical reaction, there is some entropy change. It could be positive, it could be negative. So, for example, you light up a firecracker. So there is a lot of entropy change. There's a lot of disorder created uh, when you light up a firecracker. So there is disorder created because of that firecracker. Uh, Burning a match doesn't really create a lot of disorder. I mean, you burn a match, it just burns up. That's it. It doesn't really produce a lot of disorder. So chemical reactions do two things: either heat is released or gained, or disorder is created, or it's removed from the system. It could be positive, it could be negative. Now, this delta S is kind of way more important when it comes to extracting work from a system or from a chemical reaction. And I'm going to give you an example. Like if I give you an example, how do cars operate? Because we have these cars running around. So we know that cars run on fuel. Let's ignore electric cars for a second. Cars run on fuel, and the fuel is like if you've got high octane petrol. So let's say cars are running on octane. So how do cars actually run on octane or run on fuel? Uh, a lot of people actually think that if you burn petrol, so octane is C8H18. That's usually a large component of what petrol is. If you burn it, there's a there's a chemical reaction that happens, and carbon dioxide and water molecules are produced, and there would be 8 CO2 molecules produced and 9 water molecules produced, and there would be 25 by 2 oxygen molecules that would be consumed in the reaction. So here is octane burning. You're burning petrol, and a lot of heat energy is produced. Right? You burn petrol, and a lot of heat energy is produced. ठीक है? And hopefully everyone knows that you burn petrol, a lot of heat energy is produced. But the thing is that heat energy is completely useless. The car has nothing to do with that heat energy. And that heat energy that's produced when you burn petrol, that's kind of completely useless. You have radiators in your cars which have water in them, and those radiators are constantly trying to remove that heat energy. So this heat energy that's produced is kind of completely useless. It's not used anywhere. I mean, it's completely pointless. The car doesn't really work on that, uh, and it does nothing. It actually is harmful for the car. It's harmful for the engine. So you have to constantly remove that heat energy. The reason why the car runs is that when you burn octane, a lot of disorder is created. Or I mean, I'm not going to use the word disorder. Entropy increases, and that is exactly why a car runs. It runs because of entropy change, and I'm going to show you how. Like cars have pistons, and those pistons, they make the car run. Just one second. So you've got these pistons, and these pistons will help the car run. You add a molecule of octane. Let's say this is a molecule of octane. Okay? So you added one molecule of octane, and assuming that the car engine is at a higher temperature, so there's going to be 8 carbon dioxide and 9 water molecules. So all of a sudden, if you burn this octane molecule, right? Octane is liquid, petrol is liquid. So all of a sudden, when you burn it, 8 carbon dioxide molecules are going to be produced. So all of a sudden, you have, I mean, let's say these are 7 and 8. So that octane molecule turns into 8 carbon dioxide molecules, which are gaseous, and 9 water molecules. Let's assume that they are also gaseous. So there would be 9 water molecules. That single octane produces a lot of disorder. It produces 8 carbon dioxide molecules and 9 water molecules. So a lot of gas all of a sudden is created. And what would all that gas do? There's a lot of disorder being created. And gas particles have high energy. They would travel at very high speeds, and they would push against the walls of the container, and they would move the piston upwards. So imagine if that disorder was not created, then it would be impossible to move the piston. So is this idea clear?
Yes.
Okay,
Yes, sir.
so the thing is, most of the mechanical systems around you, they actually need high entropy. They want they work on entropy change. The heat energy that's released or given off or taken in, that's most of the time it's completely pointless. You don't want that. Your car engine, it would have been ideal if burning petrol produces no heat. That would be an ideal fuel. Like you burn petrol. I mean, the only reason you're burning petrol is because it's increasing entropy. Uh, and the disorder that's in. I mean, if you have more gases, more disorder, the piston moves up. So that's how mechanical work is produced. So entropy increases, more gas molecules are created. So more gas molecules are created, and disorder increases, and that's why your car operates.
Sir, for this delta H would be negative, right?
Which one?
matlab for this reaction, because entropy is increasing, so delta H would be negative.
Delta S or delta H?
Delta H.
Delta H is negative. Enthalpy, heat energy is being produced, so that's negative. Okay? But delta S is positive, right? Ibrahim, is this clear?
Uh, sir, matlab delta S positive क्यों हो रहा है?
Delta S positive means okay, disorder is increasing. That's what we learned. Like, what is delta S positive? High entropy, it's going from a low entropy state. You had liquid octane. Okay, that's petrol. You've seen petrol, right? It's a low entropy state, and all of a sudden you burn it, and it produces a lot of gas molecules. So it moves to a high entropy state. Okay,
ठीक सर.
so Ethan, you got this. Sohail, Kausab, is this clear?
Yes.
Maybe is this clear?
Yes.
Yep.
So just remember that. So burning a match, it's kind of completely useless. It just produces heat. You can't really turn a match into useful work. I mean, that's because burning a match doesn't really create a lot of disorder. I mean, you have a match in your hand, and once it burns out, you still have a match. The only thing is its color changes. Not a lot of disorder is created, but burning petrol kind of creates a lot of disorder, and that's exactly why steam engines worked. How did steam engines work? You took liquid water. I mean, that was an endothermic process. That was a highly endothermic process actually. So you took liquid water, and you provided it energy, and it turned into gas. So your steam engines also pretty much ran on the same system, that all of a sudden you had this liquid water, and you were able to move trains using this. So that's how your steam engine operated. So all of a sudden, the liquid water in the piston, it changed into gas, and the particles, they increased, the disorder increased, and the piston started to move. So that's why we are very interested in delta S. That's one of the reasons. Delta S is way more important than delta H. So ideally, you want delta H to be zero. You don't want, I mean, you don't want anything to do with the energy change that's happening. You don't care about the energy change. You want it to be zero. That's, I mean, the thing that's wrong with steam engines is that to convert liquid to gas, it requires a lot of energy. Uh, so, which is why, and that's the same. The issue with with fuel is kind of the opposite. It releases a lot of energy, and in both cases, the energy is kind of pointless. You don't want both of them. So ideally, you want enthalpy change to be zero, but you want a very high delta S. You want the delta S to be as high as possible. Uh, but not very high, because if it's very high, then it's like a bomb blast. It's like an explosion, uh, which is why things explode, because the delta S is extremely positive. You don't want it to be extremely positive. You just want it to be. You don't want to explode the system. You don't want to create so much disorder. So, which is why you won't use a nuclear. I mean, nuclear fuels are actually used, but you have to control the delta S in that case. So, anyways, how do you? So we figured out why delta S is important. Now, what we need to figure out is how do you measure this delta S? What's the way of measuring delta S? Now, this is not really part of your course, so I'm just going to give. I mean, there's a version of this formula that's part of your course. So for that, I'm just going to tell you this formula. I'm going to explain this formula a bit. Uh, Remember, when delta S increases, the sign of energy and delta S are actually the opposite. I mean, let me explain this, and this is also very important. You see, delta S was positive over here, right? So work was produced. When work is produced, that means, I mean, the piston was moving, the work was produced. So that means work is exothermic, right? I mean, work is energy, right? So that means that the two ways energy is produced. One is heat energy, that's the enthalpy change. The other one is the mechanical work that's produced, and that's also work. That's also measured in. I mean, if you know physics, that's also measured in joules. So work is being created, it's being produced. So that's exo. So you get the point. When delta S is positive, the work that is produced is exo. Is this clear to everyone?
Yep.
Yes.
Yes, sir.
Okay. So remember this. The signs are kind of the opposite. Delta S is positive. The system would produce useful work, mechanical work, which is why it's going to be exothermic.
So can you explain it again? I didn't get.
When delta S was positive, right? So what was happening? Disorder was being created, right?
Ji.
So what was the system doing? It was producing useful work, right?
Yeah. Yeah.
So
Ji.
when something produces work, that means it's
No,
exothermic.
it was not producing. It was using that word.
It's producing work. I mean, it's giving the work to whatever outside. I mean, what is the
Huh.
reaction? What is the reaction doing? It's releasing energy in the form of work, in the form of mechanical work. Okay, is that clear?
Ji. Yes, sir.
So which is why it's exothermic, right? So just remember that I'm going to write it over here as well. I mean, that's why you have a negative sign. Mike, please off, Carlo. So you've got. So remember this delta S. If it's positive, that means useful mechanical work is produced. Hence, energy would be exothermic. Remember, this is not the energy that was related to enthalpy change. This is the energy this is the work done that's being produced because of entropy change. So that's why basically you have a negative sign over here. That if energy is exothermic, the delta S would be positive. So which is why you have to add an extra negative sign to make it positive. So that
लेकिन इस डेल्टा एस में इन दैट डेल्टा एस में फर्क क्या है मतलब
which
why
one?
are both of them having the मतलब ये डेल्टा एस पॉजिटिव आपने जहाँ पे लिखा हुआ है तो why do we get negative sign मतलब वहाँ पे डेल्टा एस
नहीं, this one.
नेगेटिव का तो मतलब नहीं है जी
Manjita, what's the sign of energy? Energy is exothermic, right? If delta S is positive, right? Okay, so what would be the sign of energy? It's going to be
पॉजिटिव नहीं
the
नेगेटिव
negative, right? So let's say delta S is positive. Let me give it a value. If delta S is positive, 100 joules of energy is work done is produced. Let's call it minus 100 joules, okay? Because it's exothermic. So if I put minus 100 over here, and there's another minus sign over here, so delta S is actually going to come out to be positive.
पॉजिटिव
Okay, so which is why the two things have opposite signs. So which is why you need an extra minus sign, because if you want to convert this into delta S or delta S into this, the sign has to switch. Is that clear?
yes
So delta S is positive, work is produced. That's exothermic. So the sign has to switch. The Ethan, is this clear? Mohammed, Zebi, Zohaib, is this clear?
Yes.
Okay.
Yeah.
Yes, sir.
Okay, now the point was, what is this formula? This is the formula. I mean, what this formula is. I mean, how do you measure entropy? Entropy is basically of a substance. For example, I want to measure the entropy of steam. So entropy is that at a particular temperature, how much work would be produced, delta Q. This one, this is the work. I mean, if you know physics, it's P delta V. P delta V is going to give you work done. Uh, Pressure of the gas multiplied by the change in volume, that would give you the work done that's being produced by the steam over here. So entropy is basically the two ways of looking at this formula. It's basically the useful work done. Okay, that's Q. That's delta Q. Useful work done at a particular at a specific temperature. So if I want to figure out how much work would be produced by steam at 500 degrees centigrade, so I'm going to take temperature as 500, and I'm going to figure out how much would the piston move, how much useful work would be produced by steam at 500. Similarly, so we can do this. So this is what the formula is. That's how you measure the entropy change that's happening. It's the work done by the substance at a particular temperature. It's the useful work done by the substance at a specific temperature. So is this clear?
Yes.
Another way to actually look at this formula is, now there's another way to actually look at this formula. It's basically a ratio of energy with respect to temperature, right? It's basically useful work done with respect to temperature. So when do you think entropy would increase drastically? That the work done that's being produced is a lot and the temperature is not increasing. Uh, so you don't want the temperature to increase. You want so it's kind of another way to look at this is that entropy is kind of the ratio of energy over temperature. So it's the ratio of energy over temperature. That's another way to actually look at it. How much useful energy is being produced at a particular specific temperature. So for this, I'm going to tell you one thing that when a system has energy, okay, any system, it has energy, like steam has energy, right? The energy has two forms. Like you have steam and it has a specific amount of energy. The energy has two forms, or it could go into two things. One is that particular energy goes into the kinetic energy of the particles. So it goes into the kinetic energy of the particles, and the particles, they start to move. Uh, they increase their speed. But the disorder, the entropy would not really increase much. So, why would it not increase? Because, and one example is you have water, and water is at 10 degrees centigrade, and now you have water at 80 degrees centigrade. So if energy goes into the kinetic energy of the particles, then temperature would be increasing. But the disorder really isn't increasing much. Uh, I mean, the disorder is pretty much constant. When would disorder increase? The disorder would increase that the system has energy, and that energy is used into the breaking of bonds or intermolecular forces.
सेम मतलब पहले केस में why won't entropy increase? क्योंकि if temperature is increasing, the particles will मतलब start colliding and they will start acting more vigorously.
Nee, but
Won't the disorder increase again?
nee, but what when I'm talking about disorder, okay? For example, think of it this way. Let's think of ice. Okay, there's solid ice. Solid ice says that the particles are arranged in a very orderly manner. Okay, so this is ice. These are four particles of ice, and let's say it's at minus 150 degrees centigrade, right? And you give it energy, and the temperature increases to minus 10 degrees centigrade. मुझे बताओ, what happened to the disorder of the system? Or was there much change?
No. Yes.
I mean, the particles would be vibrating a little bit harder. There would be more. There would be more vibration, but I mean, they would have more kinetic energy. But the disorder is not changing. ठीक है? I mean, the particles would not be able to sort of push the piston upwards. ठीक है? So they're not able to. There's no delta S positive. There's no useful work that would be created. Is that clear?
Yes.
Yes.
Okay, so and that pretty much happens with the metal. I told you, like if you heat a metal at minus 100 would still have pretty much the same entropy as it would have at 1500 degrees centigrade. It would become red hot, but the disorder would pretty much be still the same. Achha, anyways, so when a system has energy, two things happen. Either the temperature starts to increase, the particles have more kinetic energy, so the temperature is increasing, but not the disorder. To increase the disorder, what do you have to do? The energy has to specifically go into breaking of bonds or intermolecular forces. When that happens, that is when delta S increases. That is when entropy increases. All of a sudden, entropy increases. So that is exactly what happens at 0 degrees centigrade, because all of a sudden the temperature stops increasing. The temperature becomes constant because all the energy is going into breaking of the intermolecular forces of the bonds between water molecules. So delta S starts to increase. So most of the time, what happens is that if you see temperature increasing, then that kind of indicates that entropy is not increasing. But if you see temperature stopping and the system has energy and the temperature is not increasing, that kind of indicates that all that energy is actually going into the breaking of bonds, and that also indicates that there's going to be a drastic change in disorder. Okay, is this clear?
Yeah.
Yes, sir.
Okay, so one way to actually understand this formula is that's the ratio of energy to temperature. You give us a system has energy and its temperature increases, right? So the ratio pretty much remains constant. That means entropy doesn't really change much. On the other hand, system has energy and the temperature becomes constant. So that means disorder is increasing. I mean, the energy value increases and the temperature remains constant. That indicates that delta S would increase drastically. Is this clear as well?
Yep.
I mean,
Yes.
that happens with a metal. Like if you heat a metal, it gains a lot of energy, but at the same time, its temperature also increases. So that kind of indicates that energy did not actually go into breaking of bonds. It only increased. The metal just became red hot. The disorder did not increase. But if you talk about water, you give it energy. Let's say give it energy at 100, and you keep giving it energy. The system gain energy. There's a lot of energy present, but the temperature is constant. So that means the ratio would increase drastically. There's going to be a very large change in delta S. So so coming back to this formula, this is just conceptual things. No one is going to ask you about this. The only thing that I was interested in about this formula was uh, that if I want to figure out the work that is produced at a specific temperature by a specific entropy change, then that work would be minus T delta S. I mean, this is something that you should know. That if I want to figure out that a certain entropy change is happening, and I want to figure out how much work would be produced at a very specific temperature, then it would be T times delta S, and that would give me the useful work that would be produced or consumed. It could be both. It could go both ways. It could be positive, it could be negative, depending on the sign of delta S. So, I mean, this is the formula that you should be worried about. So this is work done, whether it's produced or taken in. That depends on the sign of delta S. I mean, if delta S is negative, then this would automatically become positive, which means it's taking in work. If delta S is positive, then work done would be negative. It's going to be exothermic. So work done due to delta S at a specific temperatures, at a specific temperature. So is this clear?
Yeah.
ठीक है,
Yes, sir.
this is not that important. It's just conceptual things. What's more important is this part. I just wanted to derive this formula. So just remember, uh, energy or useful work that is produced due to entropy change, that's minus T times delta S. So we're going to continue with this. Just remember this formula. That's it. Uh, and remember how to figure out the sign. Why was entropy change actually? Why do we study entropy change? That's what we did, and why it's important. And in the previous class, we did figure out how to predict the sign of entropy change, whether it's negative or it's positive. Today, let's continue tomorrow. And
Okay, thanks.
okay, then everyone take care. Allah Hafiz.
Sure, sir,
Allah Hafiz, sir.
Thank you. Thank you.